Great. How's everyone doing? My name is Wayne Gilmore. I'm the Executive Director of Research Computing here at Boston University. And with me I have Emre, who's the Research Data Officer at Harvard University. And Scott Yockel, who's the University Research Computing Officer at Harvard University, could not make it today. He's feeling under the weather, but I'd like to thank him for giving me the opportunity to speak in his place and help him out here. So today we're just going to talk about a couple of the other building blocks, right? So how do we enable research computation for all the researchers at the universities that we support? And there's three areas here I want to talk about, is just generally research computing and what is research computing, and then sort of the transition that we're going through right now, and that is accelerating in terms of the shift between traditionally supporting HPC type workloads to supporting cloud workloads for the research community. And then where do we go moving forward? And arguably one of the big things now is data. What do researchers do with all that data? So Emre's going to talk about the Research Data Connect program at Harvard University that they're working on developing, that really works with not only research computing, but libraries and research administration. All three components are very important in helping researchers really manage that ecosystem of their data as they do their work. So many times people focus on hardware, compute, storage, and arguably those are super important things, and they continue to evolve, especially in the world of AI. But I would say that in the support of research, probably one of the most important things are the people and the facilitation that happens between the people on research computing support staff and the researchers themselves. And here is, you'll see that this is kind of formalized around 2014 with the ACI REF program that the NSF has funded, and it has grown into essentially a whole professional organization, so the Campus Research Computing Consortium, CARC, that essentially is a large virtual organization of research computing personnel that really are there to support each other and in sort of move the process forward in research computing facilitation as a profession. So what do research facilitators do? And what they do really is they work very much directly with the researcher, and they co-learn and co-create with them. So many times a researcher will have a very interesting research problem that they come to us with, and they know that they need a lot of computation and a lot of programming and application support to do it, but they don't really know how to do it and how to figure it out. And a lot of times these research problems are very novel, so we have to actually work with them and learn with them and create with them to do these products. And arguably, the research facilitation field covers all the technical and support areas, right, of supporting research and research computing. So systems engineers, application developers, application support people, and service support people. And many times they have to all work in tandem with a researcher or a researcher's lab to help them solve their problem and move their research forward. So it was probably one of the most important things, and it very much differentiates research computing somewhat from traditional enterprise IT, although I would argue that enterprise IT is starting to fall into this paradigm as well. Whereas enterprise IT really just provides services to the masses, but research computing has to provide customizable services, right? And to really meet specific research needs. So here's just a slide sort of reiterating for most people that know what high performance computing is, right? And you know, high performance computing traditionally has been fixed computing environment that is deployed over a scheduled system. So researchers will submit their jobs, they have to wait for those jobs to run, they get results back, right? And typically command line interface, although nowadays we have extended the HPC landscape using products like Open On Demand to provide web front ends, right, to HPC clusters, which has been very well adopted. And very much tailored to parallel processing, GPU computing, messaging fabrics like MPI, and being able to move bits and bytes between nodes very quickly. So those are all kind of the traditional aspects of high performance computing. And a good example is like a quantum chemistry field, right? So when you have a 10,000 by 10,000 matrix, that requires 10 to the 45th combinations of analysis, you're going to really need a parallel architecture system and application layer to be able to do those type of calculations. And this is essentially what very large-scale high-performance computing is doing for the research community today. And how has research computing grown? So this is essentially the work we do at BU. On the left here is 2013, what our HPC landscape looked like, and we had less than 1,000 researchers using our system, and doing maybe 10 million CPU hours a year. And these starbursts essentially show the amount of usage on log scale by the different departments in the university, right? And in 2023, we're almost up to 100 million CPU hours a year, supporting 3,000 researchers. But more importantly, we've probably supported departments in every single college in this university. So that really speaks to the breadth of research computing, where you have people in fine arts, hospitality, and so forth, and they all need the cycles, they all need the computation, and they all need that facilitation expertise to really help get their work done. So this has really exploded across all research domains, and so it's going to continue to grow, and we're going to have to continue to support it best we can. You also see that we're servicing a lot of students, so increasingly faculty want students to use the same type of systems that they're computing on, whereas today, we're supporting over 50 courses on our cluster with over 2,200 students. But the nature of research computing is changing. We've done a very good job at trying to add additional things to the HPC framework so that people can do graphical work, people can use web browsers instead of command line interfaces. But there's going to be limitations to that in the type of environment that a typical high-performance computing cluster can provide. And so we need to adapt with the times, like everyone else. So why is there the shift, right, from HPC to cloud? And so, HPC to cloud essentially is how do we go from a, fixed computing environment to a very dynamic environment where researchers and developers can actually build analytic tools that could be used by not only one research group at a university, but shared and used by researchers all over the world, right? And instead of having to, use schedulers to submit your jobs, how do you really get on-demand computing and storage accessible to you so that you can do the work on the fly that you need to do? So there's very, and then there's also oh, sorry, that was the wrong slide there. Oh yeah, on the right, excuse me. There's always the basis for product development as well. The work we've done with Red Hat in leveraging their data science environments and providing that to researchers to be able to get their work done. So these are examples of the type of workloads, right, that aren't very well supported in high performance computing, but could be very well supported on cloud type infrastructure. And everything from burstable resources. So we only have so many resources here on campus. How do we burst into larger resources and be able to give those back quickly? How do we support systems and cloud research, which a large part of this workshop is about this week? Traditionally, that has been very hard to do, not only on HPC resources, but very difficult to do on commercial cloud resources because you're working in a black box. And then how do you support not only one data science platforms, but the numerous data science platforms that will come about and be developed over time that cater to very research domain specific communities. So, back in 2018, BU and Harvard Research Computing envisioned an open source cloud environment that we could work on, that we could put in production that researchers could use and serve research in the academic communities. And really, this is built on a very solid foundation that has grown over time. So as Gloria alluded to this morning, there's the MGHPCC, which was very pivotal right, for the 5 institutions that are part of that consortium to really stage research computing, work on collaborative projects, and really start working on providing more shared services to the entire community, not just to one university, right? And then on top of that, we leveraged Northeast Storage Exchange, which provides us large data store, both in terms of Ceph data and tape archive data. And then on top of that, we have NERC, right, which is going to provide software platform, infrastructure as a service, data science platforms that can be easily accessible by researchers and the education community in a very federated way, right? So if you're at one institution, you can access these resources just using your login credentials for your institution. Another institution can do the same. So how do you make that access to those resources very easy to do? And then the interesting part about a production cloud service is that we can really leverage all of the work that the Mass Open Cloud Alliance and Red Hat has done over the past decade, right, in terms of development of software, such as OpenStack, OpenShift, and the Red Hat data science environment. And what we can do is, as those products are developed, we can actually start exposing those to the research community, provide valuable data back to the developers on the MOC Alliance side and the Red Hat side that they can learn from. And there's this iterative cycle on how do we continue to optimize sort of those products and really cater towards the use cases that researchers and academics need over time. So it's pretty novel in that approach, in that we can expose these technologies to the research community, and it's worked pretty well. And you know, this has essentially been backed by a lot of investment by a lot of parties. So we have the MJHPCC, which is really a $90 million investment by the 5 universities in the state. We have the NESI project was backed by a $5 million NSF consortium, and we're now self-sustaining in that service. And then also industry partners. Red Hat's listed here, but there's many more industry partners that have contributed a lot of additional things as well to make this success. And then currently, who's using NERC? So NERC is being utilized by almost 70 investigators right now, 11 institutions, and you can also see the breakdowns of disciplines. Right, so this will over time look very much like that starburst, where we're servicing pretty much all domains on NERC to be able to get research done. And then a couple of projects that are leveraging cloud right now. The first one here is the PCAN, which is the Predictive Ecosystem Analyzer project. This is out of BU, essentially a science framework built on RStudio that runs ecological forecasts for students and professors. This is using the NERC OpenShift environment and Red Hat OpenShift AI platforms. You can see the components on the right-hand side here. And I'm going to turn it over to Emre now, who's going to discuss a project that's going on at Harvard and research data comments.
Thank you, Wayne, for doing the difficult part of the talk. So I want to talk about a couple of things what we built at Harvard. But before that, I want to answer the question, which one is the king, data or the compute? I might be a little bit biased as the data officer, is that the answer is data. But with a minor footnote saying that the data you don't do compute on is trash, you are paying money to keep. So what are we doing with this data? This is NSAF group. They hold, last I looked, about 95 terabytes of data. They have data from air pollution, they have data from census, they have very highly regulated data from Centers for Medicaid and Medicare. They combine all of this to see people living in dirty air, does that affect their health? And their studies are one of the only explicitly cited studies in EPA policy change. EPA changed their air pollution policy because of this study. And it has been shown that this study increased life expectancy up to 7% for adults 65 and over living in polluted air locations around the US. So this is why we do this, right? We are doing this so our researchers come up with this research that actually affects real life. What they have is, they used to have all these flat files, 95 terabytes of flat files. But what they're doing is now they're using Apache Airflow. They put this into a database. They look at the database using Apache Superset. They pull data from this database. They do analysis on it. They do compute. And they come up with their results. So beyond the tech, why not we let researchers build everything? I'm sure there are researchers here, so sorry, but if I let researchers build all of this, it will be a mess. So we need to build this and give it to them. So what's the problem? What this thing that we are trying to build? If you think about a very standard data lifecycle, there is a lot happens before we actually start doing the compute, right? And we know that compute is the king. So what do we need to do to get to the part where we do the compute? We have to do planning. We have to do what data we are going to get, where are we going to get it from, who is going to pay for that data, is the data regulated, what are we agreeing to while we're getting that data, how are we going to keep it safe? If we don't plan these from before even the project starts, it's going to cost double when we hit the compute part. We need to make sure that we can store this data. We need to make sure that we can do data management on it. I bet $5 to anybody here, if you go to a researcher and ask what is their biggest data management problem, they will say that I don't have enough storage. And you tell them that's not data management. So we need to tell them how to better manage their data. It's been shown repeatedly that better managed data leads to speedier output of research. That is, researchers publish quicker, they publish more papers, which gets them more grant funding, which lets them publish even more. So we need to let them know that, you know what, at some point you need to manage your data properly, and naming things, for example, metadata, et cetera, et cetera. So the problem we see it is that we need to give them easier way to manage their large data set. Large data set, what means a large data set changes from research domain to research domain. We ask people, and if you ask a digital humanities person, 1 terabyte is a huge data set, whereas our astrophysics department has 20 petabytes. They think that, no, it's okay. So it doesn't matter how much data they have actually. You need to teach them, you need to show them, and you need to give them tools how to better manage their data, right? Even if you have 1 terabyte data, if it doesn't have metadata in it, you are not going to be able to manage that properly. We need to share this data. We need to make sure that it's reproducible, because one of the biggest crises in science right now is people cannot reproduce other people's research, even if they have all of their data. We need to get in front of that. Half of my job is dealing with retention compliance issues and dealing with the federal government. And we need to do this for the researchers, right? I never met a researcher who loves to do paperwork for government. And we need to tell our superiors metrics about who uses this data so we can get more funding to better build systems for our researchers. So the problem, and this is the vision we have in Harvard Data Connect. We changed it from Data Commons to Data Connect because everybody started using Data Commons name, and we didn't like that. It's a combination of services from different parts of the university. It's a combination of them with application, with tools. All of these needs to be integrated. And then we have offices at the university who does compliance, funding support. We even think that research computing should help researchers go find funding. And all of this together comes in this picture. We think that it should be service-oriented. That is, our system should have different services that can be plugged in when necessary. It needs to be modular. As you can see here, there is a lot going on in the background, but what the researcher needs to see is just one web portal, right? They need to log into one place where their data is, where they can do compute with their data, where they can search it, where they can share it, right? Because if you tell a researcher you need to go 5 different systems to do 3 things, they will not do any of that. And lastly, I wanted to show this picture of the vision that's put underneath the data lifecycle to show you that it takes a village to manage research data, right? Because for planning, you need help from, for example, libraries. Libraries are really good at user support. For compute, you need our HPC systems. For actually keeping this data when the research is done for many purposes, we again go to libraries. Libraries are really good at keeping information for a very long time. They did it with books for hundreds of years. Now they are retooling their systems to be able to keep data repositories where this research is deposited and kept for long times, right? So combination of all of these services, all of these people, and then all of these applications, right? We're going to hear from Stefano about Dataverse. Dataverse is a huge part of our vision because we need a very good data repository to keep all of this research data. And we need tools, again, we're going to hear our space, right? We need tools to be able to give researchers so they can have easy management tools for their data. Thank you.
I guess one thing to just, you've talked about what you're doing and what you know. I mean, part of this is we have broad community systems researchers and industry and stuff. What is it that we're not doing? What is it that you really need built from combination of industry and systems research from the MOC team? What is it that we can, that's big gaping holes in what you have?
I won't come out with the laundry list. There's lots of things that are needed, but you know, I think continued application development of platforms, right, that many researchers in many domains can leverage, that can be easily taken by facilitators and adapted for specific research use cases, right? I think those are probably the most important things going forward. And I think goes into the data too, right? Can you have common frameworks to manage data for the research community as a whole? Because right now, in the research computing space, we're chasing our tail, trying to figure out where all this data lives, right? And all of the different platforms that are storing it, some of which are no longer going to be free, and where do we put it all, right? And how do we manage that going forward? You know, to Emery's question, if you were asked a researcher, what is the data that you have? Most researchers don't know because they just let it collect over time, right? And so being able to better understand what data a researcher has, how it's being used, those metric types of frameworks are going to be very important going forward. So, and helps us to report up and get more funding, really is the most important thing. Hope that helps answer the question.
Yeah, I can keep going. I mean, so one of the, I'd say, big impedance mismatches that we've had, you know, is the difference between research computing traditionally, you know, where you might have a compute cluster and a bunch of people get free use, and then you get buy-in if somebody has too much of it or something, versus coming from the world of cloud, I've always felt like we got to charge people for what they're actually doing, where they get out of their competitive grants and actual, rather than us deciding as an IT organization. You're now several months into kind of buying into this model now, I think, Wade, but I'm curious how you'd sort of relate that. Do you think, and actually for you, Emery, do you think that this model of figuring out how we charge people the real cost, not artificial cost, but the real cost of what things take, how important is that to what you view as the future of this?
So I'll give my comments and I can hand it over to Emery. I'm a very strong believer in democratization of access to compute. And sometimes that means you have to give that away for free or someone has to subsidize that use. We would not be where we are today if we did not have central subsidization to provide access to compute to the research community at the university. So there's always going to need to be that level. Who pays for it? That's another question, right? But yes, services do need to be paid for. They need to be written down and they need to be put in a proposal budget so that the national funders can actually fund those activities. And what you're seeing now, right, with NIH, specifically NSF is going to follow in data management policies, is they're building these line items in where you can actually put costs to manage your storage and manage your data, which goes to Emery's point, right? So I think that is going to be important to be able to support those models that charge, but we need to be able to provide access freely to the community as well.
Thank you. Yeah, I mean, that's a great question, because at Harvard we built a highly regulated data environment, very secure. Sure, very secure. It took us 1.5 years to build. And our biggest problem right now is how are we going to charge people to pay for this, right? We had meetings after meetings for over 1 year, and right now, I think after 1 year, we are not even at the place where we started for making a decision. We are going backwards to make a decision who's going to pay for this. The problem is that, for example, when you build this, it's in cloud, right? We have certain fixed costs, right? We have people to run this, we need people to run this, we need software to put it on it, and then we have the variable cost of researcher actually using it and charging compute. The variable costs are minuscule compared to actually running the thing, right? So I can run this without any researchers on it. It will cost as much as if I had 3 researchers on it, right? So what am I going to tell the researcher when they say, if I weren't on this, you are going to pay this still, you have to pay this to run this thing, right? So you have all these costs. So what I can pass on the researcher so that they can put on a grant is so small. When you tell the researchers, it doesn't make sense to them, the scales. So what's remaining, I cannot charge the researcher for that because I have to pay this to run the service, even if they weren't on it. And they tell that then you need to subsidize this, right? And then I have to subsidize it with central funds plus funds from the schools. But then one school says, I have 1 researcher, and they say the school B has 5 researchers on it. Why am I paying the same subsidy as school B? So you have to deal with those issues as well. So it's a very thorny issue that we are dealing with, how to charge for this. And I mean, at the end of the day, one very good comment was that this is a federal requirement why we have to have a secure compute environment. If the government is requiring this from our researchers, why should our researchers pay for this, right? So then that's why I said at the very beginning, we are now behind the first meeting that we have to decide how we are going to charge for this. So I mean, basically, I have no idea how to charge for this.